Modern high-performance compute clusters rely on decoupled reactive data movers. Because these systems route around congestion only after a bottleneck has formed, they frequently leave high-cost processors idling in a state of stranded compute. The health of these networks is dictated by a massive array of variables: rapidly fluctuating queue depths, PCIe saturation levels, and memory tier states. As clusters scale, interacting infrastructure variables increase until the system hits a mathematical wall, the curse of dimensionality. The system's joint probability space becomes exponentially large. It is mathematically intractable for standard commercial hardware to hold, update, or query this data in real time. Since the hardware cannot calculate the exact state, it relies on reactive heuristics. These guesses lead to network microbursts and job stalls that leave multi-million-dollar GPU clusters unproductive. Lumentum's Predictive Tensor Control Plane, or PTCP, is a different approach to infrastructure management designed specifically for this data scale. PTCP moves away from traditional static network graphs and standard pathfinding algorithms, which are often too slow to prevent congestion in AI workloads. Instead, the architecture treats infrastructure telemetry as a probability tensor. It uses the principles of Tensor-Network Quantum Gravity to model the data center as an adaptive information geometry. The core logic involves compressing high-dimensional telemetry into tensor trains. This allows the system to predict the fabric's next geometry and route traffic along holographic geodesics before bottlenecks can manifest. Under this framework, routing becomes an emergent physics problem focused on optimizing a dynamic, differentiable space. The Lumentum optical circuit switch, or OCS, is built on a foundational rule. The control software must never interfere with the physical optical light paths carrying the payload. This requires a clean separation between the optical payload and the brain of the switch, an x86 control plane running the sonic operating system. The system ingests data using eBPF kernel space probes. These probes act as lightweight hooks that sample the environment with near-zero CPU overhead. Crucially, these probes only observe management interfaces, control plane calls, and security signals. They never inspect the optical payload itself. This provides the continuous, high-dimensional telemetry stream required for predictive modeling without degrading the performance of mission-critical optical paths. Raw telemetry variables are first normalized into a discrete state space using kernel density estimation. This creates a massive joint probability tensor representing the system's pattern of life. This tensor is far too large for standard memory to hold, which is why the system utilizes a specialized slow path execution for model updating. Using Tensor Train decomposition, the system compresses the massive tensor into a sequence of interconnected three-dimensional tensor cores. As new telemetry arrives, these cores can grow in size, a challenge known as rank inflation. To keep the memory footprint bounded, the system periodically applies singular value decomposition. This truncates negligible probability states, slicing away data that doesn't impact the cluster's behavior. This compression pipeline allows an otherwise impossible mathematical model to reside directly on standard local hardware, ready for microsecond querying. With the model compressed, the FastPath Edge agent can query conditional probabilities in microseconds to determine the best routing decisions. To turn these probabilities into hardware actions, the PTCP framework maps classical networking variables to the physics of Tensor-Network Quantum Gravity. In this framework, geometry is not a pre-existing field. It is an observable reconstructed from the entanglement state of the network. The system calculates an effective bond dimension for every link based on bandwidth, queue depth, jitter, and trust levels. This source image shows how entanglement capacity is mapped into area and distance. Link capacity dictates mathematical area, while the inverse of that capacity defines the physical distance between nodes. Under these rules, bandwidth and latency become the raw materials used to compute an emergent information metric, weaving a mathematical spacetime out of cluster telemetry. When bottlenecks or congestion occur, they manifest as geometric curvature on this tensor network, as seen in these concentric variation rings. The FastPath agent predicts these gravity wells by forecasting the fabric's next operational geometry before the traffic actually arrives. The routing algorithm then identifies holographic geodesics. the optimal paths that curve around these areas of topological stress. By treating the network as a differentiable space, the Lumentum OCS stops reacting to port states and begins actively optimizing optical paths for specific AI workloads before congestion can form. Network operators are often hesitant to grant an automated AI unchecked authority to rewire an optical core, fearing aggressive changes could cause destructive network oscillation. Every routing decision is forced through bounded actuation, a hard-coded projection clamping hardware responses within a safe envelope. The system utilizes a champion-challenger framework. A live champion executes safe actions, while a quarantined challenger learns new baselines safely in the background. To address reliability, the system uses conditional value-at-risk optimization. This mathematically penalizes high-tail, worst-case outcomes, like synchronized congestion that could leave a GPU cluster idle. Bounded actuation and CVAR ensure that hyperscalers get the benefits of predictive routing while guaranteeing the fabric never enters an unsafe or unstable state. This geometric model also provides a new way to handle zero-trust cybersecurity. Instead of matching static signatures, cyber attacks are now identified mathematically as local topological defects in the network's geometry. Most AI controllers are black boxes, but the PTCP architecture provides human operators with TNQG residual diagnostics. These residuals turn high-dimensional telemetry into explainable metrics, like bottleneck surfaces and localized stress points, so operators can understand exactly why the switch is making specific decisions. This capability shifts Lumentum's business model from one-off hardware sales to a recurring software subscription. By packaging tensor compression and TNQG physics into an auditable control plane, Lumentum creates a revenue stream rooted in proprietary intelligence and optimized AI cluster economics. At this scale, the value isn't just the chassis.